By the late 1920s, aviation had hit a hard ceiling. It wasn't a barrier of aerodynamics, lift or drag, it was a barrier of chemistry. At sea level, an aircraft engine is a predictable machine. It ingests air, mixes it with fuel, compresses it, and ignites it. But as an aircraft climbs, the environment changes. By 15,000 feet, the atmospheric pressure drops significantly. The air density is roughly 60% of what it is at sea level. For a naturally aspirated piston engine, this is catastrophic. The engine is an air pump. Its power output is directly proportional to the mass of oxygen it can process. At 15,000 feet, the engine is effectively being strangled. It is drawing in the same volume of air, but that volume contains only half the oxygen molecules required for efficient combustion. To understand the problem, we must look at the intake stroke. The piston descends, creating a partial vacuum. Atmospheric pressure pushes air into the cylinder. At sea level, that pressure is 14.7 pounds per square inch. This pressure differential fills the cylinder rapidly. At altitude, that pressure might drop to 8 or 9 psi. The pressure differential is too weak to fill the cylinder completely before the intake valve closes. This creates a state of low volumetric efficiency. The fuel injectors, or carburetors, continue to deliver fuel, but without sufficient oxygen mass, the mixture becomes rich. The result is incomplete combustion. The explosion inside the cylinder lacks thermal energy. Brake horsepower drops. A 500 horsepower engine at takeoff might only produce 250 horsepower at combat altitude. The aircraft becomes sluggish, slow, and vulnerable. The physics were clear. To fly higher, the engine needed sea level pressure at 20,000 feet. Engineers in the 1920s understood the requirement: forced induction. They needed to compress the thin air before it entered the engine. The industry standard solution was the mechanical supercharger. A mechanical supercharger uses a centrifugal compressor driven directly by the engine's crankshaft via a train of gears. The concept is straightforward. The engine spins the compressor packs the air, and the density is restored. However, this solution introduced a parasitic load. To compress air to the necessary pressures for high-altitude flight, the supercharger required significant torque. To gain 100 horsepower in altitude performance, the mechanical supercharger might strip 30 or 40 horsepower from the crankshaft just to spin the impeller. The net gain diminished the higher the plane climbed. Furthermore, the gear trains required to spin the impeller at 20 or 30,000 RPM were heavy, complex, and prone to mechanical failure. The industry was trying to solve a thermodynamic problem with brute mechanical force. It was inefficient. At General Electric, the approach was different. The focus was not on taking power from the crankshaft, but on recovering power that was being thrown away. Nathan C. Price was an engineer focused on the efficiency of steam and gas cycles. He, alongside the GE team, looked at the other end of the combustion cycle, the exhaust. When a piston engine fires, only about 30% of the fuel's energy is converted into mechanical motion. Another 30% is dissipated through the cooling system. The remaining 40% leaves the tailpipe as heat and velocity. This is high enthalpy gas, waste energy, dumped into the atmosphere. Price's engineering objective was specific. Utilize the kinetic and thermal energy of the exhaust gas to drive the compressor, completely decoupling the system from the crankshaft's mechanical output. The concept was the turbo-supercharger. The architecture is deceptively simple. The hot exhaust gases exiting the engine at high velocity are routed through a nozzle box. These gases impact the blades of a turbine wheel, forcing it to spin. This turbine is connected via a solid shaft to a compressor wheel located in the fresh air intake. As the turbine spins, powered solely by waste gas, the compressor spins with it. It sucks in thin, high-altitude air, compresses it to sea-level density, and feeds it into the engine. Thermodynamically, this is elegant. As the aircraft climbs, the atmospheric back pressure on the exhaust drops, which actually makes the turbine more efficient. The higher the plane goes, the faster the turbo spins, and the more air it compresses. It is a self-regulating feedback loop that theoretically maintains sea level power regardless of altitude. The theory was sound, the mathematics worked. But in the late 1920s and early 1930s, the reality of materials science was about to collide with Price's design. The exhaust gas leaving a high-performance aircraft engine can exceed 1600 degrees Fahrenheit. In a piston engine, the internal components are cooled by oil, water, and the cyclic intake of cold air. The piston gets a break every cycle. The turbine wheel gets no break. It is subjected to a continuous, relentless blast of supersonic, superheated gas. At the same time, it must spin at 20,000 RPM. The centrifugal force pulls at the turbine blades with tons of force. Steel turns plastic at these temperatures. It undergoes creep, a slow, permanent deformation under stress. In early tests, the turbine blades would simply stretch until they struck the housing, or the metal would soften and shear off completely. The engine would ingest the shrapnel, or the casing would rupture. Price had a mechanism that could deliver the air, but he didn't have a machine that could survive the process. The turbo-supercharger was capable of flight, but it was also a self-destruct mechanism waiting for the throttle to be pushed. In part 1, we defined the problem. Aircraft engines suffocated above 15,000 feet. We also identified the theoretical solution, the turbo-supercharger, a device that used waste exhaust energy to compress intake air. But theory had hit a wall. The exhaust gases required to spin the turbine were hot enough to soften steel. The centrifugal forces were strong enough to rip that soft steel apart. Nathan C. Price and General Electric didn't just need a design, they needed a metallurgy that didn't exist yet. To understand the failure, we have to look at creep. In standard engineering, steel is treated as an elastic material. It stretches under load and snaps back. But above 1000 degrees Fahrenheit, the crystal lattice of the metal begins to slide. The deformation becomes plastic. It is permanent. A turbine blade spinning at 20,000 RPM experiences a load roughly 14,000 times its own weight. If the metal temperature hits 1500 degrees, standard alloy steel behaves like taffy. The blades would stretch by a fraction of an inch, just enough to hit the casing. The resulting friction created a thermal runaway, leading to catastrophic disintegration. Price faced a binary choice: cool the exhaust gas or find a metal that ignored the heat. Cooling the gas was inefficient. That heat was the energy source. They had to change the material. The breakthrough lay in non-ferrous alloys. The team turned to materials originally developed for medical implants and cutting tools, alloys like Stellite and Vitalium. These were cobalt-chromium alloys, not steel. They maintained high tensile strength even at red heat, but they were notoriously difficult to machine. You couldn't cut them, you had to cast them to near-perfect shape. This required precision investment casting, the lost wax process, adapted for industrial scale. Price and the team also redesigned the mechanical stress points. They developed a method to weld these exotic alloy blades to a more ductile steel rotor, allowing the center to handle the torque while the edges handled the heat. They also introduced cooling caps, small baffles that directed a stream of ambient air over the turbine nozzle box to keep the casing temperature within survival limits. With the turbine finally holding together, a new problem emerged on the intake side. The ideal gas law states that as you compress a gas, its temperature rises. The turbo-supercharger was compressing the thin stratospheric air successfully, but in doing so, it was heating that air to over 300 degrees Fahrenheit. Hot air is less dense than cold air, By heating the intake charge, they were undoing the very density gains they were trying to achieve. Worse, injecting 300-degree air into a piston engine triggers pre-ignition, or knocking, which can destroy a cylinder head in seconds. The solution was the intercooler. It was a radiator for air. Price and the engineers had to route the hot, compressed air through a heat exchanger exposed to the freezing slipstream of high-altitude flight. This cooled the charge back down, restoring density before it entered the carburetor. Validation was brutal. GE strapped test engines to the beds of trucks and drove them to the summit of Pikes Peak, 14,000 feet up, to run them in thin air without leaving the ground. Then came the flight tests. The failure rate dropped, the Stellite blades held, the intercoolers kept the intake temperatures manageable. By the late 1930s, they had a machine that could theoretically allow a bomber to fly at 30,000 feet, well above the effective range of most anti-aircraft fire and enemy fighters. But solving the engine problem created an aircraft design problem. A naturally aspirated engine is compact. A turbo-supercharged system is a sprawling industrial plant. It requires the engine, the turbocharger, often mounted feet away in the wing or fuselage, the intercooler, and yards of high-pressure ducting. Every foot of ducting added weight. Every bend in the pipe reduces airflow efficiency. The exhaust pipes had to contain 1,600-degree gas while running past fuel tanks and aluminium wing spars that melted at 1,200 degrees. Furthermore, the pilot needed control. If the turbo spun too fast at low altitude, the engine would overboost and explode. Price had to help perfect the wastegate, a valve that regulated how much exhaust gas hit the turbine. It was a complex feedback system that the pilot had to monitor constantly. The engineering worked, the materials survived, but the complexity of the aircraft had doubled. The turbo-supercharger was no longer an accessory, it was the central organ around which the entire aircraft had to be built. The question was no longer, can we fly high? It was, what happens to warfare when we do? By the late 1930s, Nathan C. Price and the General Electric team had achieved the impossible. They had turned a self-destructing experiment into a reliable component. The turbo-supercharger was no longer a theory, it was hardware. Now, the question shifted from, does it work, to, what can we do with it? The answer would define the air war in Europe and the Pacific. The data was starting. Without a turbo-supercharger, a standard 1,000 horsepower engine would produce only 400 horsepower at 25,000 feet. He was asthmatic. With Price's system, that same engine could maintain 1,000 horsepower, called military-rated power, all the way to 30,000 feet. This was not a marginal gain. It was a vertical expansion of the battlefield. It allowed heavy aircraft to operate in the thin, cold air of the stratosphere, where aerodynamic drag was significantly lower. This capability dictated the design of the most iconic aircraft of the era. The Boeing B-17 and the consolidated B-24 were built specifically around this technology. These bombers were flying power plants. They could carry heavy payloads of ordnance over vast distances because they could cruise high and fast. Without the turbo-supercharger, the strategic bombing doctrine of the US Army Air Forces would have been physically impossible. The planes simply couldn't have carried the weight over the Alps or into Germany. It wasn't just bombers. The P-38 Lightning was one of the few fighters to use this system. Its distinctive twin-boom shape was largely a result of engineering necessity. The designers needed space to house the massive GE turbo-superchargers and the long runs of ducting required to cool the air. It was a fighter plane wrapped around a plumbing diagram. Because of this, the P-38 could outclimb and perform better at high altitude than almost any contemporary fighter, which relied on simpler, less efficient mechanical superchargers. Tactically, altitude was armor. In the early years of the war, German anti-aircraft flak batteries struggled to target aircraft moving at 30,000 feet. Enemy fighters, utilizing mechanical superchargers, saw their performance degrade rapidly above 20,000 feet. They became sluggish, while the turbocharged American bombers retained their power. It forced the enemy to redesign their entire air defense network. They had to develop larger cannons, better radar, and entirely new jet and rocket aircraft just to reach the altitude where Price's engines were operating comfortably. But the most profound impact of Price's work wasn't in piston engines at all. It was in what came next. Look closely at a turbo-supercharger. It has a compressor. It has a turbine. It handles high-temperature gas dynamics. It is, in gasoline, half a jet engine. The metallurgical data, the cooling cap designs, and the blade stress calculations that Nathan Price and GE perfected for the B-17 became the foundational knowledge for the jet age. When the United States needed to build its first jet engines, they didn't start from zero. They started from the turbo-supercharger. Nathan C. Price is not a household name. He didn't fly the planes. He didn't drop the bombs. He simply solved a thermodynamics problem. He found a way to take the energy we were throwing away and use it to push us higher. He didn't invent flight. He made high-altitude flight mechanically reliable. And in doing so, he changed the shape of the sky.